This is lecture number 13 of the course AU 203 Statistics and Quality Control. In this lecture, we will go into the one of the important discrete probability distribution that is called binomial distribution. Okay, before understanding binomial distribution and its probability mass function, we need to understand what is actually called as binomial random variable or Bernoulli trials. And then we will go into the deriving binomial distribution and its probability mass function as well as its cumulative distribution function. And then in the end we will see the shape of the binomial distribution. Okay, let's say first thing we need to understand now is what is we know what is random variable. Now we will be going into a particular type of random variable, what we call it a binomial random variable. As you know, from bi means two, nomial means terms, binomial means two terms. Okay, now we will see that we have a coin which is not fair, because if it is a fair coin, then the probability of getting a head is 50% and probability of getting a tail would be 50%. But here we have little twisted. The probability of getting a head is 60% and the probability of getting a tail is 100 minus 60, that is 40. Okay, let's say if we have such a coin and we flip that coin and the random variable here is the number of heads we received after flipping 10 of the coin. So it could be x could be 0 times we get head, or x could be 1 times we get head, x could be 2 times, or up to 10 times we could get head. So x here is a random variable which could take any value from 0 to 10. What is random variable? Actually, random variable has 4 characteristics, 4 attributes. The first attribute, which is an important one, is you perform an experiment. For example, you're just tossing a coin or picking a card from a pack of cards. Whatever you are doing is your number of the trials should be independent. So the outcome of one of the trial does not have an the probability of that outcome does not depend on to the probability of the previous outcome. So it means trials must be called independent, and we have already seen is independent events. So and we already have seen what is event and what is an experiment quite in detail. But here the trials, one of the first attribute is for a random variable is the trials must be independent. Second thing is the outcome of your trial would have only 2 possible outcomes. Just like tossing a coin, either you get a head or you get a tail, or in short we can say one of the outcome is either success or failure. So if you have such a random variable, it means in which in each trial the possible outcomes are either success or failure. So such a trial would be called as a binomial. Such a variable would be called as a binomial variable. So first condition independent. Second, the outcomes are either success or failures. Third thing is number of trials are not infinite. So there are some finite number of trials. So let's say if n represents the number of trials, then n must be a finite number. The fourth condition is whatever the possible outcomes are, there is certain probability associated with these 2 outcomes, either with a success or failure. So if the probability of success in first trial is 60%, then obviously in the second trial is also 60%. For this particular coin, which is not a fair coin, then it means that either the probability of failure or the probability of success remains same in each trial. If these four conditions are satisfied, then such a variable would be called as a binomial random variable. And binomial obviously comes from the possibilities that either it has a success or a failure. And here P is representing to represent the probability of a success, and 1 minus P is actually equal to Q, which is representing the probability of a failure. And because there are only two possible outcomes, so if any variable is observing these four conditions, then such a variable would be called as binomial random variable. So if you see, the X is the number of heads you receive after flipping that particular coin 10 times. So this satisfied because each and every trial you are flipping it 10 times, and every trial would be independent, and either you get head or tail, so you have two possible outcomes. And then obviously you are flipping it finite number of times. Here the number of times is 10, and the probability of success, let's say for first trial, is 60, then the second trial is also 60, the third trial would also be 60 to get head. So the probability is not going to change. Then such a variable would be called as a binomial random variable. And such trials in which we are dealing with binomial variables are called as Bernoulli trials. So Bernoulli trials always involve Bernoulli variable. Okay, now let's see, you need to find out which of the following is a binomial random variable. For example, the number of patients to which particular drug is effective. So you see, the drug which has been effective to the first patient, which has nothing to do with the second patient. So it satisfies the first condition independent, and obviously the possible outcomes are whether the drug is effective or whether it is not effective. So there is no such thing between two outcomes. And third is the number of patients to which this drug is given is also finite, and let's say the probability of effective or is not going to change with the trials. Then in this way, the variable, for example X, which is representing, or Y, or whatever letter we use to represent, which is representing the number of patients to which this drug is effective, so that variable would be called as a binomial random variable. Okay, another example is the number of cars sold by a salesperson in a week. So this number could be a variable because it could be 1 car, it could be 0 car, it could be 4 car, it could be 5 car. So and you see it satisfy all these four conditions. The probability of selling it to the first person has nothing to do with the probability of selling to the other person, so it is independent. And the first condition is satisfied. Second is you have whether you will be able to sell it or you will not be able to sell it, so the two outcomes. And the third is you are selling the finite number of cars, and so this could not be an infinite number. So it is satisfying and the probability of selling it or not selling it would be constant. So it is satisfying all four conditions. Then this variable would be considered as a binomial random variable. For example, you have a standard pack of card and you are picking two cards from that, and the number of kings you get. So for example, in pack of 4 cards, in a pack of 52 cards, you have 4 kings. So and what you are doing is, once you pick a first card, and then you are not changing, you are not keeping it, but you are replacing it back. So the probability of getting a king is, let's say, 1/4. So because there are 4 kings in the 52 cards, so 1/4 is the probability of getting first king, and second king also 1 by 4. But once you don't replace it, then it will not be called as a binomial random variable. It is only binomial random variable because it is satisfying all these 4 conditions when you are without replacement. So uh, uh, if uh, if it is replacing it, you are keeping it with yourself, then once you pick first king, then the probability of getting the second king would be different, so it won't be satisfying that the probability remains the same, the fourth criteria. So then it would not be called as a binomial random variable. Okay, for example, you have a lot of 100 capacitors, and you are interested in how many, X would be the number of defective capacitors. So X is a random variable which could take any value from 0 to 100, and as we know that here, whether it is defective or not defective, only 2 outcomes, and trials are independent and finite, and the probability of getting defective and not getting defective is not going to change from trial to trial. Then it would be called as a binomial random variable. Okay, number of defective parts in the next 25 parts produced. So obviously here the number of trials are fixed. So it is not infinite. So it must be a random variable, binomial random variable, and probably whether it is defective or not defective, 2 possible outcomes. Okay, the number of questions answered correctly in MCQ tests. So obviously you have finite number of questions, independent, as well as whether you do it correctly or whether you are successful or whether you're not successful. And the probability of because success is obviously 1 by 4 is the probability. If there are 4 options, then this probability is not going to change from trial to trial, and it would be called as binomial random variable. Okay, the number of bits in error in the next 5 bits transmitted through a digital transmitting channel. So if you are interested in how many bits having error in the next 5 bits, so it could be 0 bit having no error, or so you having an error or not having an error, and finite in number and independent, and the probability of finding error is not changing from first trial to second trial, then it means it is called as a binomial random variable. So whatever situation given for a random variable, you just need to check once it satisfies all these 4 conditions. If one of the condition is not satisfied, for example, if a number of trials are infinite, then it would not be called as binomial random variable. So all 4 conditions must be satisfied. Okay, for example, you are as a quality engineer, and you are interested in carrying out a surface scratches on a sheet of steel per square yard area. So let's say if number of scratches are 0, number of scratches are 1 or 2 or 3, and then this random variable would be called as a binomial random variable because it is satisfying all these 4 conditions. Okay, now there is a problem, and take a pause and read the problem and try to answer that. You have a company having 20 employees, and out of which 11 are females and 9 are males. So what they need is they need to pick 3 of these employees out of these 20 to go on a business trip. So the manager calls all 20 names in a hat and chooses at random. So X is the number of female X is assuming that X is the random variable, which is the number of female employees chosen. The question is X a binomial variable? So once you are choosing it, then you know you need to check whether it is satisfying the first condition, second, third, and fourth condition, and then you need to answer it. So take it a pause and to this video and try to answer it. Okay, here the answer is no, because if you pick one of the person, if it is a female, then in out of 20 there are males as well. So it is not an independent trial. Then it would not be called as a binomial random variable. Okay, see another problem. Read the problem. A certain species of tomato has probability to live after transplanting from a pot to the garden is 60%. So the probability that your tomato is successful is once you move from a pot to a garden is 60%. So botanist transplant 16 of these tomato plants. Assume that the plants lives independently of each other. So here the keyword is independent. So and let T is the number of tomato plants that live. The question is capital T is a binomial random variable. So out of 16 the number is finite, and trials are independent. It is already mentioned in this problem that trials are independent, satisfying the second condition. And the third condition is uh, the probability should not be a finite number is already there. So the fourth condition is whether the probability is same or not. So here they have already mentioned that the probability to live after transplanting is 60%, which is not going to change. So you have which remains the same. So it means in this problem T is called as binomial random variability, because this random variable is satisfying all the four conditions. Okay, third problem. In a game of luck, a turn consists of a player continuing to roll a pair of six-sided die until they roll a double, two of the same face value. So a pair of six-sided die is being rolled, and you are interested in the number of rolls in one turn. So, for example, the roll would be you roll a double means if you are throwing die, if let's say you get both two. So once you get the same number on both the dice, then it would be your successful roll. So here y is the number of rolls in one turn. So let's say the first condition is trials are independent. Yes, the trials are independent. And then there is a condition, you need to check all the four conditions. So take a pause and try to answer that question. It satisfies all the conditions except that you are continuously rolling. So number of trials are not finite. It means it won't be considered as a binomial random variable, because number of trials must be finite. So in this case, why a binomial variable which number of rolls in which you get double is won't be called as a binomial random, because it satisfies all three conditions, but it doesn't satisfy this one of the condition in which you must have finite number of tries. So you need to be very careful whenever you are dealing with binomial random variable. You must check that all these four conditions must be satisfied in order to be a valid binomial variable, or otherwise it would not be called as a Bernoulli trial. Okay, now look into this example for binomial distribution. Let's say we have an experiment of tossing a fair coin 5 times. So fair coins means the probability of getting a head is 0.5 and the tail is 0.5. So x is the number of heads in flipping flipping the coin 5 times. So it could be 0 head, it could be 1 head, it could be 5 heads. So what are the possible outcomes for these 5 flips? So let's say just represent this number of sample space is 32 possible outcomes that could come, because either you get head or you get tail. So in the first outcome, either you get head, so the number of ways of the first outcome would be 2 ways, second outcome would be 2 ways, and in the 5 trials you would be having 2 to the power 5, 32 possible outcomes. Okay. Uh, what is the probability of not getting any head in 5 flips? So how to calculate the probability that you are flipping this fair coin 5 times or you're not getting head for you're getting head for 0 times. So this is how we can represent that situation, that the probability of, because x is number of heads we got, so the number of heads has a 0 value. So out of 32, 1 upon 32 is the probability that none of the times you get head. So probability of getting x0 means number of heads you are getting 0 heads. The probability would be 1 over 32, because total possible favorable possible outcome is 1. And out of that 32 total possible outcomes, and this one can be represented in terms of a combination, because you are flipping 5 times and you are getting 0 heads, so 5 combinations 0 would be 1. Let's say if you are interested in 1 times getting head, so probability of getting 1 head would be 5 choosing 1 or 5 combination 1, and which would be 5 possible outcomes, and total possible outcomes are 32. So 5 by 32 is the probability of picking 1 head once you are having 5 trials. Second is you are interested in getting the probability that of getting 2 heads out of 5 trials. It would be 5 choose 2, which is 10, and then 3 times you get head, or 4 times you get head would be 5 choosing 4, and 5 times you get head would be 5 combination 5, because 5 times you get head as a probability of 1 by 32. So we can generalize this situation. For example, x is a random variable which is representing the number of heads in flipping how many times, k times. So it would be, this situation can be represented 5 0, 5 1, 5 2 can be represented as 5 combination k divided by 32, or 5 combination k can be written in factorial form, would be 5 factorial over k factorial divided by 5 minus k factorial. So we can say that this term is a 5 combination k, or this is another way of writing down the same combination. So this is would be the general formula for calculating the probability in that scenario. Okay, what we do is instead of having a fair coin, let's say we have such a situation in which our outcome would be the probability of success is 70%, and obviously the probability of failure would be 30%. So because we are dealing with binomial random variables, so there is only 2 possible outcomes, either a success or a failure. So let's say x would be the number of successes in 6 trials. So let's say what is the probability of getting exactly 2 successes out of 6 trials. So these are the possible outcomes for 2 successes. So for example, we are 6 trials. So let's say the first trial is successful, its probability is 0.7. The second trial is also successful, its probability is 0. And then the third, fourth, fifth and sixth trial is not successful. So it means the possibility of 2 successes out of 6 trials would be, if we calculate this, it comes out to be 0.7 square times 0.3 to the power 4, because 4 times failure and 2 times successes out of 6 trials. Let's say you have another possibility of 2 successes and 4 failures. So out of 6 trials, it could be one of the another situation in which the first trial is unsuccessful, second is successful, then the third is unsuccessful, then the fourth is successful, and the next 2 are unsuccessful. So you could represent the same situation by this manner. So how many possibility of 2 successes? We can say that out of 6 trials, so number of trials are 6 and you are choosing 2. So there would be 15 ways of having this scenario. So what we do is, since this is the probability of one of the scenario, then the probability of this is the probability of one of the scenario. So if you have 15 different ways, then we can say that the probability of 2 successive successes in 6 trials can be represented by because it is for one way, then it would be there would be 15 possible ways. Just I have shown only 2 here, but altogether it would be 15 different ways, and 15 different ways can be written as 6 combination 2. So this would be the formula for calculating the probability that we are going to get 2 successes in 6 trials would be, if your probability of success is 70% and probability of failure is 30%. And you can see that 2 number of successes and 4 number of failures are there, because there could be 15 different ways in this particular situation. Okay, we can generalize the situation. Let's say we have P is the probability of success, and we can say X is a random variable where you have, instead of 2 successes in 6 trials, let's say you have K successes in N trials. Then this probability can be written as N combination K times this is probability of success to the power the number of successes. Let's say in our previous problem K was 2, and probability of failure would be 1 minus P. Because if P is the probability of success, then probability of failure would be 1 minus P, and in the previous problem altogether N was 6 and K was 2, so K was 2 here, and 6 minus 2 it would be 4. So it would be N minus K would be the power for the probability of failure. So this is how we can generalize this particular example, particular scenario. So we say in general in N Bernoulli trials. So once say N Bernoulli trials, it means a random variable would be a binomial random variable. So the number of outcomes that contains exactly K successes equals the binomial coefficient. So that would be representing this coefficient. In our previous problem, it is representing 15 different ways of having 2 successes out of 6 trials or 4 failures. So the probability mass function of a binomial random variable with X number of successes in N Bernoulli trials with the probability of success P is given as. So we can say there is a formula, mathematical function for calculating the probability of this binomial random variable, where N is the number of trials, X is the number of successes, and P is the probability of success to the power X, and this is the probability of failure because you have only 2 possible outcomes, and N minus X. So this becomes a generic formula for calculating the probability of this binomial trial or binomial experiment rather. And there is a neater way of writing down where X is a binomial random variable, and Y because I'm using a letter B to represent a binomial random variable, and what information this random variable requires is the parameter, the number of trials must be finite, and P is the probability of success. So if you provide that information, then we can calculate for K number of successes in N trials. So this would be the formula for calculating the corresponding probability. Here number of trials are fixed because N combination K cannot be N cannot be an infinite number, otherwise it would not be a Bernoulli random variable. And since we are dealing with the 2 parameters here, so this binomial, this probability formula is going to represent certain distribution, and that distribution is given a name as a binomial distribution. And the parameters involved in the binomial distributions are the number of trials and the probability of success. And we know that we are only dealing with a binomial random variable. Okay, so let's say you have a situation in which determine the probability that a lot of 1000 capacitors contains no more than one non-conforming capacitors. So if, as it's been recent past, one out of every 100 capacitor produced is non-conforming. So probability of non-conforming would be 1 upon 100. So here X is the number of non-conforming capacitors such that X can take any value. X can take 0, X can take 1, X can take 2, X can take up to 1000. And here B is representing that this random variable is a binomial random variable or binomial distribution with number of trials are 1000, and probability of having a success here is that the part is non-conforming. The probability P is 0.01. 1 upon 100 is 0.01. So what I do is I say X is a binomial random variable with number of trials n. P is the probability of success, and the formula for calculating k successes out of n trials would be this. And this k could be a number, it could be 0, it could be 1, it could be 2. So let's say in this particular problem we have been told that calculate the probability that out of that 1000 contains no more than one non-conforming. So X is a random variable which is representing non-conforming capacitors. So X must be less than and equal to 1. So the possibility could be either X is 0 or X is 1. So if you take the sum, you will be able to calculate that probability. And probability when X is 0, you can do it n combination 0 times probability of success 0.01 to the power 0, and probability of failure would be 1 minus 0.01, which would be 0.99 to the power 1000, because your 1000 minus 0 is 1000. Plus 1 capacitor is non-conforming, then number of trials are 1000 combination 1 is number of ways by which you could have a success, and one success means one non-conforming, and 900 out of 1000 minus 1, 999 would be if other than non-conforming. Then if you take the sum, you will be able to evaluate. So it's very small probability for this term, and add them together, and you are adding up because OR rule is there. So the probability that in this particular scenario your out of 1000 capacitors you get either 1 or less than 1 non-conforming is only 0.04%. So it is very less probable, because the probability of having non-conforming is very low here. If it is 0.1, then there would be a huge difference. If you calculate with 0.1, 10% probability, then you will be able to calculate a very different number. So this is how we can use the formula for binomial distribution to calculate the probability. Okay, this mathematical relation which is representing the small f of x or p of x, which is representing the probability of a random variable, and this mathematical function gives us an output, or in output if x is a random variable, and it gives an output certain probability, and if you plot that, it would show you the probability distribution. And we know the cumulative distribution function is nothing for a random variable when which is represented with a capital F, and which is representing the probability when x is less than equal to small x, and small x is the value of that threshold. If you recall back the case of earlier we have seen for cost of different books, so less than $20 or less than $30. So less than $30 means $10, 20 and 30 all are included in that. So you need to take the sum of the probabilities to get the cumulative distribution function. So n combination x, p to the power x, 1 minus p to the n minus x. So it's a mathematical function. So the x is less than x means take the sum up to x, you will be able to get the cumulative distribution function. And uh, CDF would be actually called as the sum of the individual probability mass functions that has been calculated over the range. For example, when your random variable would be less than some threshold value small x. And for example, the distribution can be shown. As you know, this is something in an S-shaped curve like that. For example, when your number of counts, number of trials are 8 and probability of success is 0.2, and x is your random variable, and for 0 count the probability is this, for 1 count the probability is this. So 0, this one plus this one is this one, and you add them together, so eventually you got 1. So that is actually the representation of the binomial distribution. Okay, let's see, we will see solve problems in the next lecture, and we will see using Minitab we can solve such problems, and we will see by different tables we can solve. Let's say the shape of a binomial distribution. So x is a binomial random variable where the parameters involved are 2 parameters. I told you that in statistics there is actually the two classifications, parametric and non-parametric. Since in this particular formula for calculating probability we are dealing with 2 different parameters, that's why it is called as parametric distributions, and here we are dealing with 2 parameters, so it is actually called as 2 parameters. So it could be a single parameter, it could be 3 parameters, or any number of parameters. Here we have a formula given which we have derived from a given example as well, that probability of getting a binomial random variable with k number of successes out of n trial can be worked out from that formula. So this formula gives us a probability for k number of successes out of n number of trials. So the shape of the distribution is actually depending upon the magnitude of the probability. For example, in fair coins the probability of success was 0.5. So if your probability of success is 0.5, then the distribution becomes symmetric. And if the the probability is much different from 0.5, either less than 0.5 or greater than 0.5, or what you can say other than 0.5 or much different from the 0.5, then your distribution becomes skewed. For example, when probability of success is 0.5, then your distribution is very much like symmetric distribution, because the central tendency of the data or the expected value comes out to be this, and these outcomes are less probable than this outcome. But if you have p-value, let's say 0.25, which is smaller than 0.5, then you have this sort of a distribution where lower values are more probable than higher values. So for example, if these values are your scores in exam, in your MCQ test, then it means if you have a bad test, then you see more peoples would be having a small score, then few people would be having higher scores. So then once it is skewed to the right, and the right you will find very less probability, that's why it is called as right skewed or positive skewed. Sometimes it is because this skewness is onto the positive side, then we call it to be, or the right hand side is a positive side, we call it a positive skewness. Skewness term we will do it later in detail as well. And here if you see the scenario in which the more probable is to get higher marks, so the test was quite easy, and less marks, less score is less probable, it means it was an easy test, then your distribution is called as left skewed. So on the left side there is a very small probability. Then and in binomial distribution, if probability of success is 0.5, then it is symmetric. If it is other than 0.5, then it will be non-symmetric, whether it is left skewed or whether it is right skewed. Okay, solve this problem. Each sample of water has 10% chance of containing a particular organic pollutant. So you are taking fresh samples of water. fresh water samples, and getting a pollutant is 0.1 is the probability. Assume that the samples are independent. So one sample has no link with the other sample. It means it must satisfy the condition for independence. Na? The first condition is the trials must be independent. With regard to the presence of pollutant, okay, what you need to calculate, find the probability that in the next 18 samples, exactly 2 contains the pollutant. So in exam, I mean, this thing would not be given that this distribution is binomial. So after looking at the problem, you need to work out that this is related to binomial distributions. Then you need to look with whether you are dealing with a random variable, because you are interested in probability. It means you are dealing with some random variable. And then what is that random variable? The first thing is you need to work out what is your random variable. So here X is the number of samples that contains that pollutant, organic pollutant, out of 18 samples you are analyzing. So that X would be your random variable. So out of 18 samples, it could be 0 sample having a pollutant, or 1 sample has a pollutant, or 18 samples would have a pollutant. So you need to first look for what is your random variable, and that is the first step in every problem solving. Whatever random variable is, you need to specify your random variable, and then you need to look into whether this random variable is a binomial random variable. So it's satisfying the first condition that your trials are independent, and this keyword gives in the problem that trials are independent. The second criteria is it has 2 possible outcomes. So whether it is having a pollutant or not having a pollutant, and having a pollutant is 0.1, then not having a pollutant would be 0.9. And the number of trials should be fixed. For example, you are dealing with 80 number of trials, and from sample to sample, the probability of getting a pollutant is not changing. It always remains 10% is the probability of getting a sample. So it means it is satisfying the condition for a binomial random variable, and you can find out the probability using the binomial probability mass function of a binomial distribution. So we specify here that X can be considered as a binomial random variable, and parameters are number of trials, which are 18, and probability of success is 0.1. So this should be the next step, writing down. Third step is what you need to calculate in the part A, probability that your sample have exactly 2 pollutants. So X becomes 2. So in your formula, 18 n combination X, P to the power X, and 1 minus P to the power n minus X. So in that formula, you just substitute. So 28.4% is the probability that you are going to get out of 18 samples, exactly 2 would have that pollutant. So 28.4% is the chance for getting. If you have to calculate for 3, just substitute 3 here, then it would be a different number. So for every value, you will be able to calculate the corresponding probability, and that is what the feature of a probability mass function for that particular random variable, that is a binomial random variable, that gives you the probability. Okay, in second part, you have been given that find the probability at least 4 samples contains the pollutant. So it means at least 4 means the number should be, random variable should be either 4 or greater than 4. So one way of doing is, which is a lengthy way, that you apply this formula for when X is 4, then X is 5, then X is 6, and you go up to 18. So, and you get this number. Or you get it some other way, then probability X is greater than or equal to 4 means 1 minus probability X is less than 4. And X is less than 4 means 3, 2, 1 or 0. So you just need to calculate for X equal to 0, X equal to 1, X equal to 2 and X equal to 3, and take the sum. You will be able to get the same numbers. So I would recommend in solving a piece of paper, instead of going from 4 to 18, it is better to go from 0 to 3. which is 1 minus the sum of probability of x0, x1, x2, x3, and then take the sum. You will be able to calculate this probability. Okay, let's say if I give you some range that your sample should be greater than equal to 3 and less than 7, then you need to go into the range by calculating the probability from 3 to 6, because 3 is included, and less than 7 means 6. So once it is equal to 7, then you need to put up to 7. So depending upon the range, you can work out the probability. Okay, in the next lecture, I will go to show you how this cumulative probability distribution can be worked out from tables as well as from software. So this is where I stop this lecture today.